Okay, with this we jump right in to the details really. And a few years ago I heard Roger Sale, a very bright mind in our community, open a talk with docking is like a discotheque. It's all about posing and scoring. And there is a lot of truth in that, because the docking problem essentially falls into two pieces. It is about where is the ligand and how happy is a ligand in the pocket. So we have part number one, which essentially is the post generation. So when we would like to put a ligand into a binding pocket by docking, of course the obvious problem is the post generation. So generating coordinates that we propose from the computer to the user to further assess. And this first part in the docking and scoring problem has mainly been driven by a principle that is known as the key lock principle, which has been set up by Emil Fischer in 1894. And that's my own literal translation here from some ancient German that he used. Essentially it reads, to exercise chemical action, a ligand interacting with a protein must fit into the binding cavity like a key into a keyhole. From 2013 on, when we started to write a new tool that you will see later on, which is called CSAR, we have realized, well, people have realized this before, but we have embedded this. It's actually only half of the truth. We will see this later on. But definitely it's a very important thing. So optimizing the tightness of fit and making things really fit nicely into the pocket, that's definitely part of the story. There is one prominent example which is published in a book that we call the Red Bible, which I can only recommend highly, and this first edition has been written in German only, and I'm happy to show you on the next slide that there is finally a work of an English translation by one of the co-authors. So it's called Wirkstoff Design, so drug design more or less. And here it is. So it's retinol with its own surface, and co-visualized the surface of its protein, of its corresponding protein, in its transporter, retinol transporter protein. And you can really nicely see how these two surfaces nicely overlap, and there is really like a key with the rest of the key in its keyhole. So definitely keep that in mind when you deal with docking and scoring yourself. So here's the book recommendation. It's very expensive, so it's roughly 500 euros currently, so probably if you can convince your librarian to get it. That's the English version, written by no lesser than Gerhard Klebe, himself professor at Marburg University. It's brilliantly written. There are loads of examples, so if you just want to jot this down, that's really highly recommended to have around. Okay, next quick poll. Never fear, we will not have polls every 2 slides or so, but in order for me to pitch the level of explanation better, I would be interested to know, are there computational or medchems in front of me? So I hand over to Christian again to launch this poll, and please be so kind to vote this for us.
Yes, you see the question already there on your screen. Please give us a little bit of information about your background. As Marcus said, this allows us to get a better sense of the audience and provide you with the best possible level of information suitable for you. And most of you already voted. Maybe I can get a few more clicks. So I'm going to close the poll in 5, 4, 3, 2, 1 now. And here's the result.
Okay, so that's relatively unusual. So we have a very high fraction of medicinal chemists here, which is perfect, because obviously medchem would not by tradition be very acquainted with all these methodologies. 30% computational chemists, still 14% molecular biologists, and 12% others, no crystallographers this time around. Okay, brilliant. Thank you so much. We can close this poll. So a few words then about how to optimize this problem, because essentially we have to be aware that we are optimizing. We propose an algorithm in the computer to optimize something. So what does that mean? Optimization examples, for example, are ubiquitous in the financial industries. Maximize my money, make me more money, find an optimum for my money. Minimize our pollution. So also this is an optimization problem. It's not only about maximizing things, it's also about minimizing things, and pretty much the same strategies are applied there. Or pick the best network for my cell phone. If I have the option of multiple ones, so I need to optimize that one. Or who is the murderer? So what fingerprint matches best with the ones that we've found from our database? Or help me introduce this electrode into her brain during surgery. So I recently read the doctoral thesis in medicine from a colleague of mine, from a friend of mine, and that was her optimization problem. Very interesting thing where they combined pretty advanced methods with nuclear magnetic resonance techniques, etc. So all these are optimization problems, and they are so much everywhere. It's really striking. And docking is also an optimization problem, namely we would like to find the best position for a ligand given a cavity. So we want to maximize its affinity alongside finding the best possible pose. Pose generation, that means the ligand should go to a place where it maximizes its fit and optimizes the affinity. Part 2 then would be the scoring. So pose generation and scoring. So where do we start with this problem? Ideally, if we can, we should start with a good crystal structure. So not just one crystal structure. If you have the option of using multiple crystal structures, try to find out which one is the most reliable, which one is the one that reflects best your problem that you'd like to solve. If you do not have a crystal structure, then sometimes you can work with a homology model. Typically what we see on large-scale data is that results deteriorate when we use homology models. That's pretty obvious because not everything is known there. There is a degree of unknownness in homology model, and of course any further subsequent steps will suffer from that uncertainty. And if you have, or if you are in the lucky situation to have a co-crystallized molecule with that good crystal structure, then of course you can use that as kind of a starting test to see whether at all the method is able to reproduce the co-crystallized situation. Please remember, and I have a few slides on that with examples, an X-ray or a PDB structure is also itself just a modeled snapshot. So you know, it's not reflecting like multiple various protein states from various proteins, but it's essentially a modeled snapshot by a crystallographer. So there is also just a human intervention in there. It's not the always wholly experimental truth, but sometimes even crystallographers can go wrong or can be unsure, etc. And sometimes even they will annotate this in the PDB file. So it's always worthwhile actually reading the comments and remarks section in the PDB file at the top typically. So all this entails problems that are to be solved. One thing which is often discussed is density, and often people rely only on density. So they just check the density, they see the recorded density in the PDB file is lower than 2 angstroms or something like this, and then they think they are happy to go and everything is all right. So what does this really mean, density is low, density is high? So here's an example that I took from the Aztecs web pages, which is very instructive. So if you take a look here, we have a resolution of 1 angstrom here in this upper left quadrant. What we see here is we do have atomic resolution, so we can clearly see where the atoms are. But essentially what we still don't know is, let's assume that there might be a nitrogen in this 6-membered ring here, whether it's a nitrogen or a carbon, or maybe even an oxygen. So element-wise, we can't really be sure what is what. But atom position-wise, we can be relatively certain. 1 angstrom resolution is really, really good if you achieve something like this. At 2 angstroms, you already have a degree of uncertainty in here. 2.7, more so. Yeah, so that entire ring could easily be shifted by half an angstrom to the left or to the right-hand side. And with 3 angstroms, you only have roughly the orientation of that, the position of this ligand very coarsely. But it could even be entirely flipped. So this part here could be down there, and this part could even be up there. So with 3 angstroms, you really are on uncertain grounds in the most cases. So if in doubt, perhaps take another discussion with your crystallographer and check the areas where you are certain or where you are uncertain. And also there is more than just density. There are R3 factors and all these things that you might assess because perhaps the area of interest is extremely badly or extremely coarsely resolved, but other areas are very nicely resolved. So on average, this density here can't really tell you everything about your structure. So go back, it's a one-time only event, check your crystal structure and make sure that what you need is what you have. A great resource, by the way, what I found is the PDB Educational Portal. So it's a website or a few websites that actually discuss very briefly what this is all about. So if you can't recall from your early studies what an R value or R3 value is, then they explain this very briefly, and within 5 minutes you know again what it was about. So here's the website, but you'll find it if you just go to the PDB 101 website and Google for Educational Portal. You just find this. Okay. Next thing is, where are the protons? When we discuss crystal structures, we must be clear about the fact that X-ray structures usually do not have any protein information in there. That is simply because protons scatter very, very weakly. We can hardly see them with X-rays, and so we are left to predict them as good as possible. We have to come up with a proposal where those protons are. Sometimes it's pretty easy, it's obvious, because we know how carbon is coordinated, so we know where the carbon hydrogens are, the carbon bonded hydrogens are. But sometimes it's really, really difficult, especially when we have situations in which we have tautomers or different protonation state possibilities. Then we're in trouble, but the good news is that, of course, there are computer programs to assist us here. So here are a few examples where we might run into trouble. Definitely tautomerism, so for example, keto versus enol tautomerism. In X-rays, we can't really distinguish between those two, so we will have to define which of the tautomers we should go along in our modeling. Sometimes, especially when we have situations in which ligands are close to symmetric, we may run into situations that we really don't know. Is this a carbon or is this a nitrogen? So these two will more or less give the same reflection patterns in X-ray experiments, and this is especially applicable to 2 of the common amino acids, namely glutamine and asparagine, where you have an O versus an N. So let me just push this down. So you have these situations here, where you have a ketone function and an NH or NH2 function. And these two here, they could flip. Yeah? So you don't know whether this is the oxygen being an electron acceptor, a proton acceptor, or whether you have an NH2 function, which is an ambiguous function of donor acceptorship in certain situations. The next and very common uncertainty refers to pseudo-rotations. So this is especially applicable to histidines, where we have a pseudo-rotation around this guy here. Yeah, I pitched this with an arrow. So we can't really be sure whether the nitrogen is on that side or on that side, or whether this is a carbon or a nitrogen. So depending on this so-called assessment, we may go totally wrong in our docking and scoring exercise later on. So all I'm saying here is we have to pay attention not only to the quality of the crystal structures, but also we have to worry about protons, tautomers, rotations. We have to assign those, or at least check the assignment that a computer proposed to us. Here's a quick protonation prediction tools overview. So there is a tool which has been around for many, many years. That's called What If. Then there is a tool embedded in CCG's Mo, which is called Protonate 3D. There is a software called HYDE. And a few years ago, in collaboration with Hamburg University, we wrote up a tool which is called Protos. So the early Protos version in 2009. Then there is the Yasara force field suite, which has a protonation proposal engine embedded. And we recently reassessed the early Protos and augmented and improved it quite a lot, actually. And you see, not all tools perform all tasks. So sometimes tools such as What If, here is the core representative, they worry about the protein side only, but they don't take care of the ligand uncertainties at all. So with the latest Protos arrival, we have actually also covered the ligand side here, and we do this extremely rapidly so that we can afford to do this for every post that we generate or for every new proposal that you generate in the computer. So what do I mean by this? As a concrete example, we may run into situations like these. So we picked a few examples here, for example, from one of the Yasara proposals for a PDB structure called 3K3I. So here you see that sometimes these automatic proposals orient protons towards protons, which is definitely not what we want. So it's only a computer proposal. We need to check visually whether everything is all right. And we need to usually do this only once, so that time is extremely well invested. Most Protonate 3D here, for example, puts a proton towards a metal, also not exactly what we want. The old Protos has an acceptor facing an acceptor, or in another language we could say that's an unsaturated acceptor facing another unsaturated acceptor. What I mean with unsaturated will be clearer in due course when we talk about scoring in a few slides. Okay, so getting the ligand into the pocket, that's the post-generation problem revisited here. The key questions that are associated with that is, of course, if you imagine you have a protein cavity and you have a ligand and you would like to get this ligand into here, then of course we have a translational problem to solve. So we have to make this translation into the pocket, and then of course we have a rotational problem. So we have rotational degrees of freedom that we need to perform. So typically this would be an optimization problem in translational and rotational space. The good news is that more or less with a certain inaccuracy associated bond distances and bond angles are in principle known. So we have an idea of what a CC single bond length would be, namely 1.5 angstroms roughly. We know how this changes when carbon changes to nitrogen and so on and so forth. So these essentially we can look up in tables. But what we do not know at all is what will the torsions be like. So if I have a ligand composed of multiple parts here, for example, and these are rotatable bonds, so that's another part of the ligand, and that's yet another part of the ligand, then these bonds here may have rotations associated, or will have bond rotations associated with it. So that's definitely the key question. When I put this ligand in here, how will the conformation of these of this ligand look like? So we are at the end left with mainly an optimization problem in torsional space. I should mention that there are also rigid dockers out there, so-called rigid dockers, so probably best known is Fred from OpenEye. And what you there would have to do is you would have to pre-generate conformers. So you pre-generate a lot of solutions here for this these torsional degrees of freedom, and then you would put them either one by one or use something cleverer into the pocket. Somehow you would have to solve that torsional problem in the end then still. Can we somehow split up these two problems, so the translational and rotational problem? Yes, we can. We can cut the ligand into pieces. We can then place the first fragment and then solve that torsional problem. We'll see this in more detail in a second. And this is probably the most used approach to docking or post-generation in the programs to date. So it's called incremental construction, cutting the ligand into pieces at rotatable bonds, placing them fragment by fragment, and thus solving the torsional problem. So the translational and R-space optimization has also found a few clever approximations or clever solutions here. This solution that I propose here is taken from the Journal of Molecular Biology from 1996. This is the seminal paper by Matthias Rarey and his colleagues. So essentially here this describes the very first stage of placing a ligand into a pocket by just pitching this up again, by having cut the ligand into pieces. So we cut here and we cut here, and then we determine this, for example, to be the fragment number 1 that we would like to place. We call it the base fragment. So what happens here in the underlying algorithm, which has been come to reputation under the name of FlexX? So this FlexX's base placement algorithm here. Essentially, we have a ligand on this side here. So that should be a fragment number 1 of the ligand, and we see that this ligand fragment has a few so-called interactions. So for example, an acceptor interaction, a donor interaction, and another acceptor interaction here at these atoms. And 3 of these interactions form triangles, and we can use now the negative or how should I say it, the opposite interaction pattern on the receptor side and find suitable fragments so that triangles, so that triangles from the ligand side would fit the respective opposite triangles on the receptor side. So essentially that's what we do. We try to spot triangles on the ligand side and try to spot fitting triangles of opposite acceptor donorship on the receptor side, and then we have a very rapid algorithm to actually place triangles on triangles, thus answering the question, where would that ligand fragment sit? So we identify those, and then we can match these triangles here onto those triangles there. Still, what remains to be solved is that torsional space problem. We need to resolve that. So let's take a look briefly at the situation. Let's imagine we have a ligand with 3 rotatable bonds. And every rotatable bond, because we are clever, we would discretize this, so we would operate on a grid and not allow any angle, but just 100 angles per torsion. Then we would have 100 possibilities here, we'd have 100 possibilities there, and 100 possibilities there. That means that we have 100 to the 3rd points to evaluate. That's 1 million points already to evaluate, and that's quite a lot if we think about it. If we need only 1 second per evaluation, in fact it's much faster, but just to have an easier approximation and computation, but if we needed 1 second per evaluation, we would have 11 days computing time for just this one ligand placement, for just this one placement of only one ligand. That's way too much. Even if we were 100 times faster, we would still need prohibitively much time to place this ligand in here. So that's definitely not exactly what we want to do. We need to be much faster here. Yeah, so maybe I stop here for a second and call out to you guys, because that's probably pretty complicated stuff for many medchems already that are not used into these algorithmic thinkings here. So whenever you have questions, or I go too fast or too slow, then just use the chat box, and Christian is available to perhaps even answer these while I talk. If not, if these still remain, we'll assess them in due course of this webinar. Okay, so what do we do about this to minimize the time that we need? Well, essentially, we again do these things in pieces. So we have a so-called base placement phase. That's the thing with the triangles that I mentioned before. And typically we do not just generate one solution, but we generate several solution proposals here. For example, the ligand might be placed here, or there, or there, or there, or there. And then we take only the best ones and we discard the rest. So these here, and these here, and these here, these here, they are just thrown to the trash bin and we do not discard them any further. So it's a little bit like we do not think they have a chance later on, so we can discard them early on and save a lot of time by not taking along all these solutions. And then we connect the ligand there where we have cut the ligand into pieces. So for example there, I'm just picking an arbitrary bond here, it might be that one. And we connect the next fragment to it, rotating around the bond where we cut before. So for example, with these solutions here, we might arrive there or there, and so on and so forth. Again, we only take the best surviving ones. We discard these here. These are again thrown to the trash bin, and we continue, and so on and so forth. So, for example, once we have an 8th fragment added, we need one more final fragment to be added. And as you see, typically a docking algorithm like this with incremental construction will deliver not only one solution, but a docking algorithm will deliver several poses. So in the case of FlexX, typically this is around 200 poses per ligand that we generate and propose then for the scoring thereafter. Okay. Even a little bit more concrete. Here in green we have the protein, in white we have the crystallographically resolved structure, so that's kind of the solution that we would like to find in a docking algorithm. So here with this red guy we have a first fragment placement solution number 1. It could also be this way, so this could also be another solution after the base placement phase, so that means after this triangle based phase. So once we have this or this solution, we continue with these 2 or 3 or 4 or 5 proposals with the next stage. So we connect the next part of the ligand to that first placement, but it could also be this one. Yeah? And we keep on doing this, so we discard those which do not have any promising energies or which clash, such as this one here. This will likely clash, so we do not take this guy here along. And we continue with, for example, the original placement number 2 and connect here, and so on and so forth. So we keep on these solutions until we hopefully find a good solution to deliver to the user. Or, to be more exact, to actually post score if we want to post score. Okay, so protein preparation. Let's do this actually. So let's take an example and actually run through these exercises here. What we have to keep in mind is we have to perhaps also do chain selections. So for example, when we have a dimeric ligand here, we actually have to take care about the selection, whether we should go with this chain or with that chain. You will see later how perhaps software can already help us, guiding us towards which one to go on or which one not to select. So actually to prepare a protein rapidly, I would like to demonstrate this using with our tool which is called LeadIt. So I fire this up. Here it is. Okay. So you don't have to recall every little click that I do here. I just want to raise your awareness on what problems we actually have to solve here. So we load or prepare a receptor here with this button, and we take something from the PDB server here, a very known example, which is biotin in its pocket, 1 STP. So here you have a little overview of what is in the head of this X-ray structure. You can see that it's really the biotin binding protein that we want to use. Actually, the resolution here is 2.6 angstroms. Yeah? So not super good, but still we should be able to work with that. Free R values, you can also check those, or sometimes they aren't even recorded. The resolution data used in refinement is given, B values are given, and so on and so forth. So you may want to check this with your own protein. LeadIt here proposes that this guy is already a ligand in there, so that's why it's colored differently, or colored as, or drawn as in stick mode. And then we have this little wizard here in Leadit where we can take you or ourselves to the next step. Here would be chain selection. So if we had multiple chains, we could pick the ones that we would favor. In this case, we only have one chain, so that is already pre-selected, and we can continue. Cofactors, heme, etc., that we should include, we can tick here. In this case, it's biotin, our ligand, so we do not need to tick this here. And we can continue with the next stage. Here we are asked to cut out the binding site. So if we take on the entire protein, then of course for a docking algorithm it's much harder to find the proper solution because you give it more freedom. So you essentially also give it more freedom to do the wrong thing. So make it as small as possible and as large as needed. In our case, typically, we put a sphere around every co-crystallized ligand atom, or around every atom of a co-crystallized ligand, if we have one, excuse me, and the enclosing sphere would define the binding site. So in our case, it's 6.5 angstroms that we typically take as a default, and we can adjust this, make it larger or smaller, and we can continue to the next stage. So here now, the protonation is proposed. So you can see that the ligand just got protons, and likewise for the receptor actually. So all these residues here that you can unfold here, they have now been computed and proposed an associated protonation. So let me jump on an aspartame here to show you what I meant with these with this degree of freedom. So if we click on flip here, you can see that we change the element assignment to these coordinates, because in the X-ray resolution, remember, we only have density around here. We don't see the protons, we only see density, and since N and O are almost isoelectronic, we can hardly distinguish between the two, and we would have to check these. In this case, it's relatively easy because we know that the carbonyl function here of this urea part of the ligand is located here, so it's pretty obvious that there should be an NH function here and not an O function there, so that assignment is pretty clear. That would be unfavorable. So you must check about these things before you actually continue working with your docking and scoring.
Marcus,
likewise for his Christian.
While you are at this point, there is a good question in the chat box about the recommendation of the selection of water molecules, and this is also covered in this dialogue, so maybe you can cover this at this point.
Yeah, brilliant. Thanks for the question. Before I come to the water, maybe just one word as to histidines here. There is one example here. So here is that example that I referred to before. When we flip those, you can see that the orientation or the assignment of N versus C also changes. Right, now to the water question. Good point. The water dialog is just here, and waters are typically recorded as just blobs in the X-ray density, and it's often entirely up to the crystallographer to tell or to write into the PDB file that there is a water located in this area or not. What we do not know is where are the protons. So it's very difficult for us to tell the further ongoing steps. The protons should be there or there, the water should be there or should not be there, and all these questions probably should be best answered by visualizing things. So let me pick a situation, for example, down here, this guy. In this dialog here, we only show waters with at least two interactions, so two interactions with respect to the water. If I switch this to 0 waters, we can see all those crystallographically recorded waters here that are also there. So the more waters you include in your docking and scoring exercise, the more room will be occupied for the docker. So somehow it might be easier for the docker to find a proper solution when you include waters in there. However, it could certainly also be that another ligand, for example, if you do a virtual screening, that another ligand would displace this water, so it would not be wise to take this water along as a fixed possibility because a larger ligand might not fit in there. So it's a pro and con decision that I will leave in there. But still, there are again a few solutions that we can offer here. I would probably say start when you do the redocking exercise and see whether the algorithm is at all able to redock your ligand or not. Start with making it easy for the program and offer a few waters with a lot of interactions to be included, and then perhaps see whether you can, in a virtual screening, declare them as freely rotatable or even as displaceable. So what is this that I'm talking about? Let's, for example, tick this water here. I'm clicking on this water now, and you see now we have computed a protonation proposal, and we have activated this water to be treated explicitly. Explicitly means that we have just told the program for its subsequent further steps where how to orient this water. So we can't do anything about the oxygen position here because that's the one that we see in an X-ray, so we can't just shift that water around freely, but we have to stick to that. But the position of the protons are free, and we could now reassign this. We could say the protons are elsewhere, but this makes perfect sense. So this proton here is oriented towards this carbonyl oxygen of this carboxylate function. Makes perfect sense. It could also be this one, yeah, and by clicking etc. you could modify this, but if I did this all in detail now, we would just lose too much time. The other option that we have is we can say, I don't really know where the protons are, make it freely rotatable. So let the program decide on the fly where these protons should actually be. That sounds nice at first sight, but at second, it gives an additional degree of freedom to the Docker. So it makes it a little bit harder for the Docker. Yeah? If you really don't know where this orientation is, then this might be an option. But the more you know, let it flow into your protein preparation in there. Yeah? Just take along what you know. Use existing knowledge. Finally, if you're totally floating, or if you know that there will be larger ligands that might occupy that space here, then you could declare that water as being freely rotatable and displaceable in Ligand. So you could actually use this flashing mode of waters to be used further on. So as opposed to several publications out there, I would not by default propose to take all waters out, as many people do when they do a docking exercise. Make it easier for the program to find what you need, and when you're driven by your application case, by your use case, of, for example, doing larger screenings with larger ligands, then it might be worthwhile taking them out, or taking a few selected ones of them out. Okay, so time is flying. Chain selection, binding site definition, we did this. Prepping protonation, I have shown this as examples. I left these in the slide so that you can take a look later on. Docking, let's do it. Yeah. So once we have prepared everything, we say next. We say next. Now we have prepared our protein and we are ready to dock. Docking is easy in Ligand, so there is a docking button up here. We define this FlexX docking. We choose a library that we want to dock. So it's up here. There is a shortcut to the reference ligand right here under this arrow, so that we can use this co-crystallized ligand to actually dock. Here it is. We say OK, and that's all that we have to do. We say apply and dock. So now the algorithm is doing exactly what I mentioned a few slides ago. We disassemble the ligand. So essentially we take it to outer space, cut it into pieces, and then we place the first fragment, the so-called base fragment, into the pocket using the triangle algorithm, and then we connect the ligand by the bonds that we cut, rotate around those bonds, and here we are with 175 solution proposals. So there is a lot of data in here, but essentially what we need is this rank here, this rank number ring, and this RMSD value. So I go back to PowerPoint for a second and show you what this actually means. So the common criterion that is still pretty heftily used out there is called RMSD, the root mean square deviation. What is this? Essentially it's the difference between the coordinates that we have observed in a crystal structure, the difference between this one and the one that we computed. So essentially the distance here between these coordinates and averaged in a quadratic manner. So it's the square root over these weighted distances between observed and computed, experiment and computer. Typically people use thresholds there for drug-like compounds. What people get really excited about in terms of their quality is anything smaller than 0.5 angstroms. Really good is what they usually treat as something up to 1.5 angstroms, and fair would be, that should be around 2 angstroms. I used the wrong symbol, excuse me. However, there are a few problems associated with RMSDs. People criticize that it's of course size dependent. So of course with a larger ligand, a larger RMSD might be tolerated as opposed to a small fragment molecule. And sometimes there might be even symmetry artifacts depending on the programs that you use, on the implementations that you use. So for example, if a carbonyl function is switched, it might still be extremely good, but the RMSD value might be bad because inside the computer program these two oxygens are not treated as symmetry equivalent. So let's take a look at how this was here. Well, we have a really good solution here on rank 1. Of course, that is a demo example. If that doesn't work, nothing should work. But with 0.461 angstroms deviation here, we can visualize this, co-visualize this with this ligand. I'm clicking on this line here. We can see how very nicely that fit is. So we have a small deviation here in this carbohydrate chain on the western side, but the rest looks really great. And if we go down those ranks here, we will find also other solutions here. For example, a totally wrong solution here on rank 116. So here the ligand is flipped. We have this cyclic part on the left-hand side, where it should be on the right-hand side, and the other way around. So you should have a pose which has a decent RMSD as a first start and calibration of your method until you keep on going. So that's the one that we mentioned. And sometimes, of course, a re-ranking would be good. So this leads us to scoring, and scoring is one of the hardest nuts to crack in our field. Let's do a thought experiment here. What exactly is affinity that we would like to find out? What is binding energy? Well, if we think closely about it, the pure definition, pictorially here, it would be the difference between the two scenarios before binding and after binding. So we would have to worry about the difference in energies between the unbound and bound states. So here's a question for you. Is this good or bad for affinity? We have an exposed hydrophobic part of a ligand. So this here is the protein, and the protein has two cavities. It has a cavity here and it has a cavity here. And let us assume that we have a ligand which is occupying these two sub-pockets here, but there is an exposed hydrophobic part of a ligand. Keep this image in your mind, and we'll go to the next poll with this, because I would like to know from you, is this situation good or bad for affinity here? Christian, you take over.
Yes, indeed. Please give us your responses. Is it good or bad to place that phenyl ring in one or the other pocket? Okay, we got quite a few responses already. Waiting for a few more clicks. Don't be shy. We are not going to give you credits or notes afterwards. All right. Few more clicks. I'm going to close the poll in 5, 4, 3, 2, 1 now. And here's the result.
Okay, a little bit as expected. People think that's, and the majority, 40% thinks that's hydrophobic. Hydro means water, phobic means enemy, so it should not be in water. Good. Phenyl pushes the H2O away, so that's good for entropy, 22%. 7% say it doesn't matter, and 30% are just insecure, which is fair enough. Yeah? So let's look at this situation again. So we have this hydrophobic part here in the ligand. Hydrophobic, that's definitely true. It's an enemy of water, so we don't want phenyl in water. The question is this relevant for affinity, where the definition is that what matters is the difference between before and after. And, oops, I'm sorry. And this phenyl part here was already unhappy in water before binding, and it still is unhappy. So we are probably all of the same opinion that this is not something that we would like to have in a drug, because that's a hydrophobe, so the phenyl should not be sticking out into the water. But in terms of affinity, the 7% can be congratulated. In this schematic view here, it doesn't matter. So the phenyl part was unhappy in water, it still is, and there are no new hydrogen bonds that it can form or any other new interactions that it could form. So as a first approximation here, this has no contribution to affinity. And this is probably reflecting the decisive step forward in the last 6, 7, 8 years in our research domain here, that we understood that this is of enormous importance here. It has no contribution to affinity. So this guy here might be very unhappy to be taken out of water in terms of the ligand. We have to consider that. This down here, this area in the protein, might be very unhappy not to bind water anymore. This guy here might be very unhappy now to get locked into a pocket. And this water here, or this area, might be happy to be freed from the pocket now and be back in the bulk solvent. So it's extremely important that we treat these things properly in dockings, in scoring software. Here's a drastic example, an inhibitor, 3 nanomolar in activity here with, let's count, 1, 2, 3, 4, 5, 6, 7 interactions. On the other hand, we lose 2 orders of magnitude with respect to affinity. I toggle this here back and forth so that you can see we only have 1 interaction here and another one which is unsatisfied here. So this can cost us drastic energies here. And the traditional approach to empirical scoring would be to use many force fields with many parameters, weightings in there. That's the hell of parameterization. Usually these have associated problems like target limitations, etc. And that's typically not good. So there are force field, quantum mechanical approaches, knowledge-based statistical approaches. They all have their pros and cons, mainly cons. They are valid only on what you observed before. They are way too slow to compute. Still, because we don't have any much better solutions, they are all used. What we propose is a new approximation to affinity, which allows us to also visualize these affinity contributions here. Namely, we have a new system that we co-wrote in collaboration with clever people at Bayer in Frankfurt and Hamburg University in the northern part of Germany. It's all published, it's out there. So if you want to jot down this publication here, Schneider et al. From 2013 in JCAMD, volume 27, page 15. Essentially what we do is we have an uncalibrated or unweighted, untrained, so there is no alpha, no beta in front of these 2 terms here, so we have untrained systems, an untrained system of dehydration and H-bond interactions. The computation is extremely fast, and we can now, because we use an atomic increment counter here and a log P in there, you don't have to understand all the mathematics underneath, just keep in mind that there is an atomic system that we can visualize. We have now the possibility to show people actually what's going on. So for example, with this case here, where we have two binding proposals that are very close to each other, this one and this one. 4 interactions we don't really know, but the visualization tells us. So you see this is a little bit older visualization style, but you can see that the protein is unhappy on that side for desolvation reasons here. And this scoring system clearly distinguishes between these 2 situations. In our new tool that is called CSAR, we have this visualization in terms of coronas. So there are red coronas for bad contributions to affinities and green coronas for good contribution to affinity. And the larger, the stronger the contribution. So HYDE does this with its kernel, and I mentioned the advantages already, that there are no parameters, no target limitations, but of course there is more than hydrogen bond and desolvation in there, which is why we have a little pre-minimization check to make sure that we do not have clash and torsional energies there. So only if these are low, the values are meaningful, and we cannot simply capture subtle electronic effects such as sigma hole creation or something like this. The desolvation terms are much larger, such as the as well as the H1 terms. So we neglect those for now. Rescoring with HYDE, we can do this. Typically we use a few poses here and not only one, and embed this. And we will now do this using CISA. So I have fired up CISA already, it's right here. And the great thing about CISA is that it does all this protein preparation that I mentioned before in Ligand all automatically. It proposes all this. So you are left to just checking what you see. One STP is the code that we just used. So I press return here. And here's the protein. And actually everything has already been done, computed, post-scored, and so on and so forth. We don't have to worry about this. And we can now simply click on this line here to see what the scoring has to say. So we click on this line, and you see we get these green and red coronas literally after just a few seconds of computation. Let me deactivate the secondary structure visualization here so that we see what we get. So let's pick out this carbonyl of the urea portion here, and with a labeling function we can drill in and see and understand what's going on. So I selected the labeling function here in the lower right corner, and I'm simply clicking on this corner, on this atom. What we see is the ligand pays desolvation penalty, 10 kilojoules, but it is rewarded with interaction energy. Likewise for the receptor, however, the receptor pays much more desolvation energy and not exactly gets full rewardment, but almost full rewardment, which is why we are only left with 1.3 positive contribution to the affinity here. So this is why this corona is green and relatively small. This guy here, pay 7 gets 8, pay 6 gets 9. The sum of these four values means 4.2 positive contribution, so negative sign in terms of free energies, and this is why it gets a green sphere. So now with this system, you have an interactive system for assessing SAR. You can actually edit and modify, but this would now lead us too far away from the docking and scoring basics, and I would refer you to our YouTube channel or to one of our next webinars here where we explain CISA in all detail. There's the website, etc. But I want to get clear that this is now a system which not only computes but also visualizes this extremely rapidly so that you can really get hold of the rationalization of your SIR behind. Time is running out. You saw that CISA is fast, visual and easy. It runs on the typical operating systems out there, but it's made for any chemist from beginner to expert. It will be helpful for you. We are very, very convinced. So, last poll here. I will in a minute. Christian?
Give me a second. Where is the... I'm missing the chat box.
Yeah, never mind.
There it is.
Let me just
quickly
fire it up.
Here's the poll. Sorry.
Yeah, excuse me. I couldn't resist, but I needed to feed in a 10-second marketing poll because I would like to know your feedback on whether this looks interesting to you guys.
Yeah, people already start responding to it. We have to hurry up a bit because we are already getting close to the deadline.
Right.
Thanks for giving us these late responses. And I guess I'm going to close the poll in 5, 4, 3, 2, 1 now. Here is the result.
Okay, thanks very much. 35 CSAT, 23 needed. Don't know yet. We'll browse the website a little. Fair enough. Thank you for that one. I was just curious, 5%. Well, okay, obviously that's not too bad then. Thanks very much. Okay, so we're coming to an end. The summary is docking is a twofold problem, post-generation and scoring. Hopefully I could explain this sufficiently well. The post-generation is especially an optimization problem in torsional space that has to be resolved cleverly. Modern scoring definitely considers desolvation. If we do not do this, we will most likely overestimate many situations and just do things wrong. Visual docking is now easily possible. There is HYDE, that's the visual scoring that we have. It's implemented in its latest version in CSAR. It's also in Ligand, but that's a little older there. And CSAR has the, in my opinion, nicer visualization here. But Ligand has the power that you need for doing all sorts of various and very advanced dockings. But still, it's only computers, so I suggest to always keep your brains very well switched on. And with this, I should come to an end here, pointing to the next webinar. Save the date, August 18. We are very proud to have one a good friend of ours from industry, from Böhringer Ingelheim in Germany, Uta Lessel. She will speak about fragment space searches and pharmaceutical research. I'm 100% convinced that this will be a very exciting webinar. And that's my last but latest slide. With this, I say thanks for now. We will discuss questions that you have after this slide. Don't hesitate. If you want to download, here's the download page. And probably one of the very valuable links here might be our YouTube channel, where we have loads of tutorials already when you want to dive deeper in, get understanding, etc. We are present on Facebook, LinkedIn, social media. If you want to write an email, please just use our support email here, support@biosolveit.com. With this, thanks again, and I hand over to Christian to moderate the Q&A session.
Yeah, thanks very much, Marcus, for this exciting presentation.